Okay, so hi to everyone. I hope you can hear me. I'm the chair of the next section that is starting right now. So I'm Beatrice Franzolini. Hi to everyone. So it's a pleasure for me to chair this session, and let me start thanking the organizer for putting together this wonderful event. So we're going to have 3 speakers line up, and each talk is going to be 20 minutes, including questions. So I ask kindly to the speaker to stay in time, and if they would like to answer to question live, to wrap up before the 20-minute mark so they can answer to the question, but I will not interrupt you before the 20 minutes deadline. To all the attendees, you can ask a question either writing in the chat or in the Q&A box. So our first speaker is Elizabeth Bersson. She's a postdoctoral research fellow at the MIT. And thank you, Betty, for being here. And the screen is yours.
Sure, thank you. I'll just go ahead and share my screen. Okay. Okay. Okay, all's good? Okay, well, thank you. Thank you so much, Bea, for the introduction. So yeah, today I'm going to talk about covariance meta-regression. This is a project that I have been working on joint with David Dunson at Duke. So, okay, we're interested in the task of estimating.
Betty, sorry.
Yeah.
I just see a black screen. Do you mind trying to share it again, maybe?
Okay. Yes. Thank you for interrupting. Just share my desktop, maybe.
Okay, I see it perfectly now. Thank you.
Okay, perfect. Okay, so we're interested in the task of estimating a p-dimensional population covariance matrix based on multivariate data. And in general, this is a hard task to estimate a population covariance matrix accurately unless you have appreciably more samples in than your dimension p. So we're motivated by this high dimensional setting where our dimension may be on the order of the number of samples or maybe even larger than the number of samples. So often in practice, let's see, okay, thanks, Alexis. In practice, practitioners will impose structural assumptions on the covariance matrix such that you can estimate the covariance matrix with greater accuracy. However, it's often unclear which structural assumption may be most appropriate in any given setting. So we aim to make use of auxiliary information on the variables, on the p variables, which we'll refer to as meta-covariates, to aid in this task of learning which structure we should be using. Okay, so as a motivating example, we'll consider an environmental health application. Environmental mixture studies are often conducted such that you obtain measurements of exposures to many chemicals from multiple measurement sources, such as urine and blood, at a time from some number of subjects. And these chemicals are often assigned different class labels, some of which you may have heard of, like phenols or parabens, that are not necessarily representing some scientific distinction amongst the chemicals. Often they're labeled maybe for convenience or to represent like use case of the chemicals. And moreover, in these studies, we often have small sample sizes relative to the amount of data that we're obtaining, particularly when you consider the fact that we have measurements from multiple sources often. So in this work, we're motivated by analyzing the different chemicals across the different classes jointly. And we can make use of this auxiliary information being the class label, as well as other chemical properties of the different chemicals like density and water solubility, for example, to inform a covariance structure that we can shrink towards. So we will be using a factor model representation of the covariance matrix, which decomposes this p-dimensional covariance matrix sigma into a diagonal variance matrix D plus this low rank covariance term lambda lambda transpose, which offers flexible dimension reduction, which can be useful for the high dimensional data setting. So again, in practice, the accuracy of a covariance estimate can be improved by incorporating shrinkage to some structures. So I've included some citations that do this in the literature, but there are many more, and I'm happy to sort of talk about that literature more offline if anyone's interested. But again, this work often imposes some specific structure. And so we want to improve the flexibility of this framework and use meta-covariates to inform the structure. In this case, that will shrink this lambda lambda transpose term towards, which will sort of determine the structure on our covariance estimate that we are, utilizing. So a bit more formally, we'll let little lambda j denote the jth row of the factor loadings matrix, which corresponds to the variable j of our response. So independently for each row of the factor loadings matrix, we will model the row as a regression based on this vector of meta-covariates for that variable jx. So here, this gamma is a regression coefficient that we'll learn, and x is our given vector of meta-covariates. So for parameter estimation of this covariance meta-regression prior, we can place semi-conjugate priors on all of the unknown parameters, and then with a normal sampling model, parameter estimation will proceed with the straightforward Gibbs sampler. And I'll have actually have code for that online. So, okay, we have this framework that allows us to use meta-covariates to learn a structure that will shrink our covariance matrix towards, and to build intuition on sort of how this works in practice. I'm going to now elaborate on the implications of this prior for a few special cases of various meta-covariate data types that we may see in practice. And in particular, I'll describe how commonly used covariance structures are encompassed by this framework for various encodings of the meta-covariates. And I want to highlight that the computation is the exact same, so you use the same Gibbs sampler code for parameter estimation for all of the special cases I'll discuss. And the main thing that's changing is, again, just the encoding of the meta-covariate information. Okay, so I'll elaborate on, throughout the special cases, I'll elaborate on the form of the prior marginal covariance. And this will sort of inform the structure that we're shrinking our covariance matrix towards. So for the general framework, for a mean zero population, the prior marginal covariance is given by this equation 3, which is a diagonal term, plus this term in red, which is sort of a meta-covariate regression term. So this is X, our meta-covariate design matrix, multiplied by this gamma regression coefficient that we'll be learning. And this derivation follows by laws of total variation and iterated expectation. So, okay, what does this sort of general framework look like for some default or different meta-covariate data types that we might see? So in a default regime, say we have no covariates on the different variables. In this case, we can choose to utilize what I'll call the intercept model, where our only meta-covariate for each variable is just a scalar value of 1, so sort of an intercept. And in this case, the prior marginal covariance matrix reduces to this form given by equation 4, which is a compound symmetric matrix, where the off-diagonal terms are equal to this gamma star term, which is just the cross product of a q-dimensional vector that we're learning as well. Say in another regime, we may have some categorical metacovariates on the variables. So we can group our p variables into some number of groupings, maybe q groupings, and to incorporate this information into the covariance meta-regression model, we can encode this grouping metacovariate into X as a design matrix formed based on group membership. In this regime, the covariance meta-regression prior reduces to this form given in equation 5, where the prior mean for the each row of the factor loadings matrix is the same if the variables belong to the same groupings. So this is sort of like a multivariate random intercept model based on the groupings of the different variables. So in this case, the prior marginal covariance matrix will be a block covariance matrix defined by equation 6, which is just indicating that the off-diagonal values of the prior covariance matrix are given by the dot product of these sort of random intercepts based on the grouping of each variable. And so for arbitrary metacovariates, again, there's a sort of general form of the prior covariance matrix given here, which is just based on this multivariate regression of our metacovariates. So this is the sort of general framework that we may use if we're combining various continuous covariates, for example, or maybe a combination of data types of our metacovariates. And in this framework, variables with similar metacovariates will have a similar prior on their corresponding row of the factor loadings matrix, this lambda. And in this way, these variables with similar metacovariates will have a similar like covariation behavior with the other variables in this way that we see with mean regression, that variables with similar covariates have similar effects. Let me just see how I'm doing on time. Okay, 1:13. Okay, so in the interest of time, I'm going to skip through some special cases, but you could think of different data types that we may have on our metacovariates, such as multiple categorical group membership. So maybe we have, for example, in our environmental health application, one sort of categorical covariate will be the class of the chemical, and another categorical covariate could be the measurement source. So you can encode this information into a design matrix, and similarly, a sort of interpretable form of the covariance meta-regression prior will fall out such that you can sort of get an idea of these different group effects. Okay. So returning to the motivating application in environmental health applications, again, often we have an abundance of information, and scientists will perhaps analyze, commonly they'll analyze data from the different chemical classes separately, so sort of assuming, implicitly assuming sort of conditional independence across the different chemical classes, which may or may not be a scientifically motivated modeling decision. So we want to be robust to such a decision and incorporate all the information in a joint modeling sort of scheme. So we'll analyze data from this TESSI study that was conducted a few years ago in North Carolina, and it measured chemical exposures to households with toddlers in them, and the S stands for SVOCs, which is a semi-volatile organic compounds, which are known or suspected chemicals that may be harmful, particularly to children who are like crawling along the floors and sort of get, you know, these chemicals in their mouth and eyes a lot more frequently than adults would. So it's important to understand how these chemicals interact. In this way, we can then understand their impact on various health outcomes of interest. So in this study, we have P1, 21 chemicals, measurements of exposures to 21 chemicals. And the chemicals that we have in the data set are belonging to 3 different chemical classes with various numbers in each class. Moreover, each chemical is measured from 2 different sources. There's a measurement from a household dust measurement, and then a wristband level where subjects will wear a silicone wristband, and then that wristband is swabbed and the chemical measurements are extracted from the wristband. And we have 73 samples in this data set. So scientists are interested in particular in quantifying the correlations of the chemicals and understanding how that may vary across and within measurement source. So we can concatenate all of the available information and jointly model the data from all of the classes and measurement sources with the goal of estimating this population covariance matrix sigma. So we will again utilize the latent factor model representation of the diagonal matrix plus this low rank term and use the covariance meta-regression prior. And as meta-covariates in this case, we will encode chemical class membership, the chemical, and the measurement source. So this will be sort of a multiple categorical meta-covariate regime. And you could imagine incorporating further information such as the various chemical properties of these chemicals as well as meta-covariates. So we iterate the proposed Gibbs sampler for this model until convergence, and we can get a posterior estimate of the covariance matrix. And here I'm plotting the correlation matrix just for ease of sort of understanding the different patterns amongst the chemicals and sources. And we can see that within source correlation is relatively high for both within dust and within wristband measurements. And the across source correlations are non-zero, but not as strongly correlated. And this is particularly notable in contrast to a posterior estimate obtained under sort of a maybe default comparison to our method, which is, sorry, I'm trying to hide the bar a little, okay. This method proposed by Schiavone et al. A couple years ago, where they used meta-covariates to inform the sparsity structure on the factor loadings matrix. And you can see that this posterior estimate has a lot more zero sparsity than our estimate. And this is sort of encoded in the prior framework. So to sort of elaborate a bit more on the differences of the different methods, we can explore in simulation what the different approaches look like in terms of frequentist loss. So in our simulation study, we look at some different regimes and simulate 25 data sets from a multivariate normal population. And in particular, we look at a few regimes, one where the variables are highly correlated, one where the variables have a block correlation structure with 3 different groups, and one where the variables have a Kronecker structured framework. And I'll just go through quickly that we compare the covariance meta-regression prior with the intercept model, the covariance meta-regression with this sort of omniscient meta-covariate. And in particular, we can compare this to this Schiavone work, which also uses the omniscient meta-covariate, and I'll refer to that as SIS. So when the true population covariance is a exchangeable correlation matrix, the intercept model sort of has a lot lower loss than the alternative methods. And this is similarly seen in the block covariance framework. And again, in particular, if you compare that to this SIS method, which also uses the meta-covariate information, the covariance meta-regression prior has lower loss. So I think I'm out on time. So thank you very much for your attention. I'm super grateful to be here and looking forward to the remaining talks.
Thank you so much, Betsy. So I have a lot of curiosity, but I think that for stick on time, we have to move on. But if anyone has some question, you can both contact Betsy like by email, but also write right now in the chat to her. And I will move to Deborah. Thank you so much, Betsy. Hi, Deborah. So our next speaker is Deborah Sulem. She's assistant professor of data and statistical science at the Università della Svizzera Italiana. And Deborah, the screen is yours.
Thank you. Can you hear me well?
Yes, perfectly.
Okay, perfect. So I will try to share my slides. Can you see it full screen? Or maybe not yet. Can you see my slide?
Yeah, perfectly now.
But I cannot go back. Sorry, I will change the mode to slideshow, maybe. Yeah, right. Okay.
Perfect.
So yeah, thank you very much, first, Bea, for organizing this session to this wonderful event and for giving me the opportunity to talk. I'm truly happy to be part of this celebration of research from women in data science and statistics. I think it's a very influential event and very beneficial for the whole community. So today is a very happy day for data science, as the Nobel Prize of Physics has been awarded to the inventors of artificial neural networks, which once more showcase the influence of data science and statistical methods in other sciences. So today in this talk, I will present a topic that I really like because it actually mixes several topics which I found particularly exciting. The first one is graphical modeling, which is statistical methods for inferring partial dependency structures. The second one is the analysis of high-dimensional data, which is the setting of many practical applications of data analysis and which poses both computational and theoretical challenges. And the last one is Bayesian inference, which for me is a framework that conceptualizes uncertainty and also provides pragmatic solutions in data analysis. And so these all three concepts makes my title Bayesian graphical modeling in high dimensions. So in a large part of this talk, I will actually present the topic in general, but I will at some point present some of my recent work with some of my former colleagues from Pompeu Fabra University, David Rosset and Jack Jewson, who is now at Monash University, and to whom I'm very grateful to because they introduced me to the topic of graphical modeling. And I would also like to give a special thanks to Judith Rousseau, who is not involved in this project, but who was my PhD advisor in Oxford and who introduced me to the topic of Bayesian inference. So let's start with the statistical problem. We will assume that we observe some vector variables, which coordinates are indexed from 1 to p. And our goal is to estimate the partial dependency structure or the partial dependencies, which means the joint conditional law of every pairs of coordinates in the vector y. And so this is called graphical modeling because a very visual and interpretable way of understanding these pairwise joint conditional laws is to represent it with a graph where each coordinate is represented by a node, and an edge represents the fact that these two variables are conditionally dependent. So in this simple example with three variables and two edges, the edge between y1 and y2 indicates that these two variables are partially dependent. And the absence of a link between y1 and y3 means that these two variables are partially independent conditionally on y2. And in general, we consider that partial dependencies are more interpretable than marginal dependencies because it can measure the direct association between pairs of variables after removing the effect of controlling variables. So for example, one measure of marginal dependency is the marginal correlation, which measures the direct or the association between two variables, which means how much one variable can help predict the other in a linear model. And in contrast, the partial correlation coefficients measure the direct association between the residuals of these two variables after regressing them on some controlling variables, which are the other variables in the vector y. So in this sense, the partial correlation coefficients capture direct dependence between two variables. And one example, one simple example is this one where, for example, from poll data, you could measure the partial dependency structure between education level, number of TV hours watched, and income. And you may find that education level is partially dependent on the number of TV hours watched, and also partially dependent on income. But income and number of hours watched of TV are independent once you have removed the effect of education level. So they are partially independent. But in a marginal dependence graph, you would have an extra edge between the two, which would mean that the graph would be fully connected. One challenge in graphical modeling comes when the number of variables that you observe is high, and high can be already 100, but in many applications you have more like thousands of variables. So for example, one prominent application of graphical modeling is in genomic studies, where it is applied to find direct associations between gene expression levels, and this can be used to understand, for example, regulatory mechanisms between genes. And in this case, the larger amount of genes that you can include in your study means that the more complex phenomenon that you can understand. The same thing also appears in another biomedical application of graphical modeling in neuroimaging, where graphical modeling can be used as a simple model for estimating the functional connectivity between different regions by inferring the partial dependencies between the level of activations between several areas or locations of the brain. And again, the more areas you can include, then potentially the more complex mechanisms you can understand. So when the number of variable p is large, then the graphical model can contain up to of order p squared edges, which would mean a very, very large model. And actually, in practice, what you want to recover is not all the partial dependencies, but the most significant one, which means that you want to find a sparse graphical model with only a small number of edges, which would be more interpretable. Another application of graphical modeling that we studied is the evolution of COVID infection rates across US counties. So for that, we estimated the partial dependencies between the weekly rates from 2020 to 2021 in more than 300 counties. And this is the dependency structure that we estimated actually after removing the effects of covariates that are known to be associated with disease evolution, such as temperature, vaccination rates, population density, etc. And so what this dependency structure reveals is that there are some direct association between the disease evolutions between faraway counties, for example, from the east to the west coast, which could mean that there are some maybe sociological factors that drive disease evolutions and can be similar in counties that are not spatially close. So how we did it? So we actually simplified the problem of graphical modeling by assuming that the variables we observe are jointly Gaussian, So they have a multivariate normal density with mean 0 and a certain covariance matrix sigma. And in this case, the problem of graphical modeling is simplified because all the partial dependency relationships are encoded in the inverse covariance matrix, which is also called precision and which I denote omega. So it's a property of the Gaussian distribution that the conditional law of two variables or two coordinates of a Gaussian vector are partially independent whenever the corresponding entry in the precision matrix is equal to 0, which means that the precision matrix encodes all the partial dependencies between the pairs of coordinates and encodes the graphical model. So our goal will be now to estimate a precision matrix of a vector of variables given some n IID observations of these variables. So if you are in the context of a large number of variables, then one way of finding a sparse model and hence a sparse precision matrix is to use penalized maximum likelihood methods. And maybe the most known and most used method for graphical modeling is the graphical lasso, which is the analog of the standard lasso method for regression applied to the context of graphical modeling. So the graphical lasso estimate is the maximizer of a penalized likelihood function, where the penalization is in terms of the L1 norm of the precision matrix. And the log likelihood is here the standard Gaussian likelihood, which is the log of the determinant of the precision minus the trace of the product between the precision and the sample covariance matrix. And the issue of this G-lasso estimate is basically the same as in regression, is that first, this estimate tends to shrink large coefficients in the precision matrix. And the second issue, which is actually for any penalized maximum likelihood estimate, is that it does not quantify the uncertainty on the graphical model, which means that it does not say how much you can be confident in the graphical model that is derived from this precision estimator. So what we propose is a method that tries to overcome these two issues, and we do that via a Bayesian method using a type of sparse prior, which is called spike and slab. And a very quick illustration of the Bayesian framework, which also has been introduced before in the previous talk. So the Bayesian methodology starts by constructing a prior distribution, which is a probability distribution on the space of parameters. And it is where the statistician can incorporate some structures, so for example, the sparsity constraints. So in this sense, it plays a similar role as the penalization function. And then given a choice of models of likelihood, one computes the posterior distribution, which is also a probability distribution on the space, on the parameter space, which from which you can derive estimator. So for example, the maximum of this distribution can be used as an estimator, but also its spread quantifies the uncertainty that one has on this estimator. So if this distribution is very peaked, it means that the data, the signal in the data is very strong and the uncertainty remaining is small. On the contrary, if this distribution is very spread or multimodal, it means that potentially the true parameter can be potentially in different areas of the parameter space. So the prior we construct is a spike and slab prior, which is constructed as follows. So the prior on the precision, on the space of precision matrices is constructed from a product on univariate distribution on each of the coefficients. So for the diagonal element, we put an exponential prior on each coefficient. And for the off-diagonal element, we use this spike and slab prior. And before I explain what it is, I just say that the actual prior on the full matrix is a renormalization of this product of univariate distribution because of the constraint that the precision matrix needs to be a positive definite and symmetric matrix. So for the off-diagonal coefficient, we have a spike and slab distribution, which is a mixture of two density. The first one is a Dirac measure at 0, which we call the spike. And the second one is the slab, which is a normal distribution that is typically have a large variance and 0 mean. And so this is a mixture between these two measures and with a certain weight theta, which is a slab's weight. And the spike and slab prior basically incorporate two desirable properties of our method. The first one is that we want to estimate some coefficient to be 0, and this is what the spikes favors. But we also want to avoid shrinking large coefficients, and this is what the slabs part allows. So how our method work? So we have to choose a couple of hyperparameters of the spike and slab, which is the slab's weight and standard deviation. And then we compute the posterior distribution, which is a real normalized version of the product between the likelihood and the prior via a metropolis within Gibbs sampling algorithm. And what is interesting about the spike and slab, first computationally, is that because it implies that the posterior distribution is also supported on sparse matrices, it means that also matrix operation in our sampling algorithm will operate on matrices of much smaller dimension if the graph is sparse, which would make the whole sampling iterations much faster. So, for example, if the true graphical model is sparse and has a maximal degree of D, which is much smaller than the ambient dimension P, then the worst case complexity of one iteration of our algorithm is DQ plus PD squared, which is much smaller than competitive methods that are generally in a P cube complexity. So how we also evaluate our method? So the output of the metropolis within Gibbs algorithms are samples from the posterior distribution. And so from these samples, we can compute marginal posterior inclusion probabilities to construct our graphical model estimates. So these marginal probabilities are simply computed by calculating the proportion of samples where the corresponding entry in the precision matrix are non-null. And from this, we can construct the median graphical model estimates by including all edges that have an inclusion probabilities greater than 0.5. Or we can construct a more conservative estimate, which is the FDR-controlled, or what I call the FDR-controlled graphical model, by including the edges with the highest marginal probabilities, such that the average of them is greater than 0.95. And so how we would also compare our methods, we will compare its inference properties in a simulation where we have ground truth by computing the power or true positive rate in the graphical model, and also computing the average marginal probabilities for the true edges. And we will compute, and we will also compare the computational efficiency by computing proxy measures of mixing time that here we consider as the expected jump distance and some chain mixing measure. So here is a simulation with P equal to 50 and with a true precision matrix, which is triad diagonal. And we will first compare our method, which is, well, called discrete for discrete spike and slab versus a previous method that used a variant of the spike and slab with a continuous spike. And here I first plot the power of the method versus the value of the smallest non-zero coefficient in omega. And what we see is that our method, the discrete spike and slab, has a better power when the value of the smallest non-zero coefficient is small. And similar observation holds for the probabilities, the average probabilities of the truly non-zero entries. We also see that the discrete spike and slab performs better than the continuous one. And this is because continuous spike and slab method fails in general to include small coefficients. Another set of simulations where we now compare the algorithmic efficiency with state-of-the-art methods that are implemented in the R packages BDGraph and SSGraph. And we also compare to approximate Bayesian methods based on quasi-posterior distribution. And what I plot here is a proxy measure of the mixing time, so lower is better, versus the computational time. And what we see in this setting with p equal 50 is that the best performing method computationally is this approximate Bayesian method based on quasi-posterior, and our method is the second best, which is quite good already because the quasi-posterior is faster, but in its inference properties are less interpretable because it cannot provide, it cannot guarantee that the estimated precision matrix are positive definite. And similar observations hold for the higher dimensional settings with p equal 100 and p equal 200. A last comment about also real data experiments. So here I show you again this example on the partial dependency structure between the residual log infection rates between US counties. And I show you again the median graphical model, and I also show you now the more conservative graphical model computed from the FDR controlled model. And what is interesting to see here is that even in the more conservative model, you still have this long distance partial dependencies between faraway counties, which means that here we can capture some direct association between disease evolutions that are not due to spatial effects, but maybe more to some similar behaviors in those countries towards health prevention measures. So in summary, so what we provided in this work is a novel Bayesian algorithm for high-dimensional graphical modeling using some discrete SPAC and SLAP prior, and all these methods are already implemented in the MOM-BFR package, which is a package for Bayesian variable selection. We compare our method to state-of-the-art and show that we had some advantages both computationally and also in terms of inference. And also we prove that our algorithms is efficient through a characterization of the mixing times, which are fast in sparse setting. So with this, I thank you very much for your attention. I wish you a very happy International Day for Women in Statistics and Data Science. And also I advertise here that I will open a PhD position soon. And so if you know some people that would be interested to apply, please recommend them to look at my research and contact me if they are interested. Thank you very much.
Thank you so much, Deborah. I will move straight away to our last speaker, Martina. Thank you for being here. It's just that we are running a little bit late in time, but thank you so much, Deborah. If anyone wants to ask Deborah some question, you can write to her in the chat. Martina is a postdoctoral research fellow. Martina Monzero, sorry, is a postdoctoral research fellow at the University of Turin. And great, I can see your screen. I think you're muted. Okay, voluntarily.
Okay, now you should hear me.
Yeah, I can hear you
Okay.
perfectly. Thank you.
Just okay. Can you see the slide full screen?
Yes, perfectly.
Okay.
Thank you.
Okay. So first of all, thank you, Beatrice, for organizing the session and for inviting me to give this talk. Today, I will present a joint work with my postdoc advisor, Professor Pierpaolo De Blasi at the University of Turin. The work I will present is about assortative stochastic block model. And I will start giving a small introduction to what assortative networks are. Then I will present to you some model and algorithms, some preliminary result, and go to the conclusion. And I hope I will manage to stay into 20 minutes. So first of all, available data in the form of network are gaining more and more attention in model research. as they are a powerful tool that can be in many applications, such as biology, medicine, economy, social sciences, and many more. Network properties are interesting from many points of view, but indeed one of the most interesting problems is community detection. The aim of my talk today is talking to you about associative network. So let me start by explaining to you with a simple yet powerful example what I mean with associative structure. So here in the figure, you can see a graph which is composed by 16 nodes, which is composed by two star-like components. In each component, we have 2 central nodes and 6 external ones. And I'm quite sure if I ask the audience, how would you do community detection for this graph, I would end up with 2 different answers. So someone could say that there are 4 different clusters, which are highlighted by the 4 different colors and the figure. In this case, for example, node 7 and 8 are clustered together, as well as node 15 and 16. I wanted you to note that there are no links between node 7 and 8, but what they share is the common behavior with respect to the external nodes. This is what we call a non-associative clustering. But a second answer I may expect is that there are only 2 clusters, which are again highlighted by the different colors. In this case, what we have is that clusters are densely connected inside and loosely connected. I mean, there are pool connections from the outside. In this case, there are no connection at all. So the idea is that when I talk about an associative network, I mean that I want the probability of a link between nodes in the same cluster to be higher than the probability of link between nodes in different clusters. So in community detection, the main interest is indeed describing the community structure. So we want to estimate the community assignment and the probability of connection between nodes. And in this direction, one of the most interesting model and most used model is indeed the stochastic block model, because it provides a powerful way to describe the generative process underlying the formation of communities. So what is a stochastic block model? Well, let's consider an unweighted and undirected graph with no self-loop. Let's consider that he has n nodes, and let's call A its agency matrix. I recall that the agency matrix is a symmetric matrix in which we have that each entry ij is equal to 1 if node I and j are connected and is equal to 0 otherwise. So what the stochastic block model assumes is that the probability of a connection between node I and j only depends on the cluster assigned of label of node I and the cluster assignment of node j. So before going into the detail of the probabilistic assumption of the stochastic block model, let's call Z the vector of the labels. Let's call P the connectivity matrix, which is a k times k symmetric matrix. And in particular, we have that the diagonal elements are the probability of connection between nodes in the same cluster, while the probability of while the elements of the diagonal are give the probability of connection between nodes in different classes. And finally, let's call P the vector of probability of community assignment. So the stochastic block model assumes that each entry of the adjacency matrix, each entry ij, follows a Bernoulli distribution with probability p that, as I already said, depends on the label assignment of I and the label assignment of j. Then we have that zi follows a multinomial distribution with probability parameter p. So given the model specification in equation 1, we can write down the likelihood whether in terms of nodes. I mean, I can have a product over all the nodes of the Bernoulli contribution, but we can also group up some of the contribution together and have a product over the possible classes, which depends on the count m sub ib and n sub ib. In particular, I will define M to be the count, MAB to be the count of all link between node in class I, A, and node in class B, while I will define N sub AB to be the potential number of links between node in class A and B. And those two quantities are important because they will be recalled back during the talk. So there are many algorithms that can be used to estimate the parameter of interest in the stochastic block model, so namely the vector of label assignment and the matrix P of probabilities of connection. But in particular, if we use a Bayesian non-parametric approach, we can also introduce a prior over K, which is the number of class in our model, and we can also jointly estimate K in the estimation procedure. An interesting algorithm in this direction is the collapsed sampler that was proposed in 2019 by Zheng and co-authors. In particular, they exploit a mixture of finite mixture prior distribution, which you can see in equation 4. So they have that all the parameters in the probability matrix P, they are IID from a beta distribution, which is conjugate with the likelihood. Then they have that the vector of probabilities given the number of classes at Dirichlet. And finally, they put a probability mass function on the integer positive number for K, which is the number of classes. Just to give a basic idea of how the algorithm works, we can summarize their work into two main steps. The first one is that they update the labels Z. They do that through a sequential procedure scheme in which they take each node I and they allocate the node whether to an existing class C with a probability that depends on the number of elements that are already in that class and the likelihood contribution of node I, or they allocate the node to a new class with a probability that is proportional to the marginal likelihood of that element. It is quite important to note that they need to explicitly compute the marginal likelihood in order to perform this update. So once they've done the label update, they can go on with updating the probability matrix P, and they can exploit the conjugacy property, having that the posterior distribution of each parameter in the probability matrix P has a beta distribution with parameter that depends on the count that I explained you earlier, so the counts M and N. The aim of our work is introduce the assortative assumption in the stochastic block model and to understand how can we modify the Gibbs sampler that I just showed you to account for the assortativity assumption. So first of all, we have to start defining what do we mean by assortativity? So which kind of definition do we want to follow? We are now working with the global assortativity assumption, which means that we ask that each element on the diagonal of the matrix P is greater than each element outside of the diagonal in matrix P, which can be stated as in equation 7. We decided to include this assumption in our model, modifying the prior distribution on the components of matrix P. And in particular, we use a uniform distribution between 0 and 1 for the diagonal element. And we have a conditional distribution for the elements outside of the diagonal, given the element on the diagonal, which is a uniform distribution between 0 and the minimum of the element on the diagonal. What it comes easily to see is that this prior specification impacts the conjugacy property of our model. So we had to modify what Zheng and co-author proposed, but we still maintain the same scheme. So we first updated the label Z. Again, we can have a scheme in which we take each element I and we choose whether to allocate it to an existing class or to a new one. Of course, the problem is that we cannot compute explicitly the marginal likelihood for each element I. So we take inspiration from algorithm A proposed by Neil in his paper, and we introduce artificially M new communities. So now we can allocate each node whether to an existing class, again with a probability proportional to its likelihood contribution and the number of elements in that class, or whether we can allocate it to one of the M new classes with a probability that is proportional to its likelihood contribution over the number of possible classes. Once we have done with the label update, we can move on to update the probability matrix P and its elements. We have to recall that, as in equation 10, now we have this constraint prior distribution, and we had to recompute the posterior distribution for the element. So we managed to obtain, we managed to compute for the elements of the diagonal that they are all independent distributed as a beta truncated variable with a domain that depends, of course, on the domain specified by the prior in equation 10. But for what concerns the element on the diagonal, they are no more independent. But we know that their joint density, posterior density is proportional to the kernel of some beta truncated distribution. So I won't go into the detail of how we managed to compute how we managed to compute that posterior distribution, but there's a way to sample for equation from equation 12. I will just present you. So this is really an ongoing project. So I will show you some preliminary results. What we wanted to understand is if there are some recovery regimes in which the estimation procedure may benefit from the assortativity constraint. So what we did is we take 6 different scenarios and 1 network for each scenarios. We took 50 nodes, 7 classes, and a off-diagonal probability of 0.2 fixed, while we changed the probability on the diagonal. We took 6 different values. What you can see here in the picture is the bias we obtain for the estimate of K, the number of classes on the left, and the adjustment index posterior distribution for on the right. In dark gray, there is our method, and in light gray, there is the unconstrained method, so without the assortative assumption. And so far, it seems that there are some schemes in which it may be worth including the assortative assumption. So just to conclude and to sum up what I presented to you today, I show you that including assortativity precludes the possibility of exploiting conjugacy property in a Gibbs update. And I show you how we address that problem. So in particular, we had to modify the label updates by introducing some auxiliary classes. And we had to modify and to compute properly the posterior distribution for the update of the probabilities in matrix P. So it seems so far that despite the computational price to pay, it can be worth including the assortativity assumption in some scenarios, but we are still working on that. In particular, we are also trying to understand if with this method, we can also deal with, let's say, other assortativity constraints. So for example, what can happen if we relax the global constraint to have a local one? But we are also trying to understand if the prior scheme that we decided to use is the only way we can have to specify the assortativity constraint, or if there are other choices, and which is the impact of the prior over the posterior distribution. So of course, every comments and suggestion is very welcome. And I thank you all for the attention.
Thank you so much, Martina. Thank you. I recall to everyone that if you have any question, you can write in the chat or in the Q&A box. And I thank Martina for being so quick, so I will not be the worst chair ever. We will be on time. Meanwhile, can I ask you like a curiosity? If I'm not mistaken, you're using these uniforms as a prior, right? And you constrain it to have assortativity. But can you have a beta instead of a uniform, or like everything changes, or?
No, I think you mean here. We can also have,
exactly.
we can, I think we can have a beta here and a beta truncated on the second part, and things should work, more or less the same. Yes.
Okay, that's super nice. It's thank you so much. And if there are no questions, no other questions, okay, I would like to thank all 3 speakers again. Thank you so much, and the organizer. And if I'm not mistaken, right now, if you're staying with the conference, you should move to room 1 because there is a keynote. And thanks to everyone.
Bye.